Hello everyone in the big wide world. I hope you're having a nice morning, evening, afternoon, whatever you're having. This is the first video of this channel, and it's also the first video in which we are going to talk about physics, about light-matter interaction. We are going to hopefully cover a lot of different topics on a quite advanced level, in this case, at least for this type of course. In the future I might post some things that are a little bit more basic, like, I don't know, the quantum harmonic oscillators, for example, of this kind of physics. In this video in particular, we are going to cover half of what is written, that you can see in the video in the top right corner. We are going to cover light-matter interaction in the semi-classical model. So we are going to have some light. This is a light bulb right here. And it's a light bulb because it's classical. It's classical light. And this light is going to interact with matter, but the idea is that we are going to quantize matter. And by the quantization of matter here, we just means that we have atoms, so we have atomic states. So we have individual atomic states, and we are going to consider the simplest case that is out there, which is the TLS, or two-level system, or qubit case, quantum bit, because it's a quantum bit of information. There are only two levels, 0, 1. We call it ground state, excited state. Alright. And so, again, light is going to be classical, matter is going to be quantized. So for this, we need to define the interaction between them, which is going to be covered in the first part of this video, and then we will also try to solve, and we will actually succeed under the approximations that you will see, the system's dynamics in the resonant case and in the non-nearly resonant case that I will define in the later. So let's start. So first of all, we need models in order to put some context in what we are going to do, because light-matter interaction is a very broad field of physics, and it's a very deep fundamental concept of physics. But here we are going to solve something a little bit more specific, but we are going to try to be as general as possible, and some of the approximations we will make in some further videos, we will relax them, and we will see how we will try to understand how light interacts with matter. And so the model is, first we need a model for our light, and you know, light is the solution of Maxwell's equations in the forms of electromagnetic waves. So they are spatiotemporal waves. They will depend on space and on time. But here we will write an electric field that will depend only on time, and we will write it such that the electric field is going to have some direction, some polarization. This just means a unit vector in the polarization direction, epsilon. There's then some kind of amplitude, and then it is a wave, right? So it will oscillate at a certain frequency, omega. And this is just a classical field. It's not a quantum mechanical operator here. Now, why I don't write that this depends on position? Because the first approximation, is a very important one that we will make, is the dipolar approximation. So now, in this context, typically one has an atom, and an atom is a proton with an electron, or maybe a lot more electrons, but we will consider kind of like a positive charge and a negative charge around it. And then an enormous electromagnetic field around it. And why I mean enormous? Because the dipolar approximation assumes that the wavelength of the light is way bigger than the atomic size. And this is typically true, right? Because the wavelengths that we are considering here, imagine it's optical wavelengths, is of the order of 10 to the 2, so hundreds of nanometers, while the atomic size is of the order of 10 angstroms, things like that. So this means that this is true, that the wavelength is way bigger. If the wavelength is so big, at the level of these distances here, the electric field is basically uniform. So this means that the only thing we have to consider in order to see how is the interaction between them is the time dependence. Or in other terms, we are evaluating the electric field that in principle depends on space and time. We are evaluating at the position of the atom. That's why we can write something like this, and we are fine with it. This is a very good approximation in general terms, and it's the first approximation one would do. If this is not the case, then we enter in another field of physics, which is nanophotonics. That is when the wavelength is at the size of whatever structure you have, in our case, and single atom. And this is a field in itself that maybe we can cover in the channel in the future. But for now, let's consider this case. So now, mathematically, let's do one thing that is very well known in quantum optics, which is decomposing the electric field that I just wrote in what we call a positive frequency part and a negative frequency part. And these are just defined as some amplitude, that is a vector here, times e to the I omega t. Omega again is the frequency of the field, minus I actually, and then another one is 0 minus, I forgot the plus here, times e to the I omega t. Now, since we write in this way the electric field, is very easy to see that, well, we have this polarization vector E2 divided by 2, and then e to the minus I omega t plus e to the I omega t. This follows from Euler's identity, right? The sum of these two is just twice the cosine, so that's why we divide by 2 and then we recover the cosine. But in this way, it's very easy to see what are these E0 plus and E0 minus. So we have this equivalence. Just decompose it. Okay. Now, let's consider the atom. What is the atom? Again, the atom is a two-level system in the energy space with some ground state and some excited state. And the energy difference between these two is going to be h bar omega 0. But we will say frequencies are the same as energy. We will say that the splitting is just omega 0 or omega naught. Alright, so one can write a Hamiltonian in this basis that depends on where we put the energy equals 0. So what I mean by that is that we say that there are two levels and the difference in energy between these two levels is omega naught, but what is actually the absolute energy of each level is not relevant. In mathematical terms, this means that we can write the Hamiltonian of the atom to be diagonal in this basis, and the Hamiltonian of the atom would be this energy of the splitting, and then we will write it in this way. So we will write it as the projector onto the excited state. This just means that in matrix form, in again this eigenbasis, this is 0, 0, 0, 1, right? This is EE, which is this thing, and there is no coupling between, for now, between excited and ground state. And we are saying that the energy of the qubit is, when it is in the ground state, is 0. We could have said, for example, a lot of people, they write this as h bar omega naught, in this case divided by 2, and then sigma z, where this sigma z is the Pauli matrix in the z direction that I recall is 1, 0, 0, minus 1. And here what we are saying is that the energy 0 is exactly at the in the middle of the transition. This is where we put the 0. In our case, we put the energy 0 here. Obviously, this is exactly the same, because you can write this Hamiltonian exactly as h bar omega naught divided by 2 sigma z, and then you just subtract h bar omega naught divided by 2 unitary matrix. Unitary no, identity is different. So this is the identity matrix. This has no physical relevance at all. So this means that we can just forget about it for the time's sake now, and just keep the projector onto the excited state. So this is the Hamiltonian of the atom. And now what happens is, as I told you, that there is a field with a certain frequency, and the difference in frequency between these two fields, this thing here, we call it the detuning, okay? And we will use it, is omega minus omega 0. And this is the detuning between the field, so the light, and the atomic transition that will play a very important role, as one can imagine. And now the first part of this lesson, or of the first part of this video, is actually to understand why the interaction Hamiltonian is the way that you will see it is. And it's easy to understand that if one considers the following. So consider a proton and an electron that are at certain distance between them, r(e), further away. Since we did a dipolar approximation, this lambda, so the wavelength of the light, is way bigger than this distance. So this means that in practice we can use this system equivalently as a dipole. So you have a point dipole. So you have a point in space that has the same electric field as the dipole in the far field. Is point light. These dipoles, by electrostatic electromagnetism, classical electromagnetism, they are defined by a dipole moment. And the dipole moment is just the charge we are considering. In this case, is the charge of the electron, so it would be minus e, times this r(e). So in this case is the difference between the positive and the negative charge, which we just called r(e). So talking about the difference in position is the same as talking about a dipole moment. This is the dipole moment. In this case, the atomic dipole moment. Alright. So now, if we have a charge Q and we submerge the charge into a field, and this is classical electrostatics in an electric field, let's say E, well, let's call it E, not E naught, let's call it E, then we know that the energy due to the interaction of the charges at the point R, the interaction of the charge with the electric field, sorry, that's what I mean, is the charge itself times the electrostatic potential at that position. This follows from the actual definition of the electrostatic potential. So the electrostatic potential is defined, so this is true. Now, if this electric field is uniform, as the one that I just wrote here, then we know that the electric field is equal, by definition, to the gradient of the electrostatic potential. So if this is uniform, this means that the electrostatic potential at the position R of the charge is equal, basically, to minus the electric field times the position. But this position, by the way, don't confuse it with r(e). R(e) is the difference between the position of the charges that we will arrive. Now we are considering a single charge right now. So R is just the position of this charge that we are considering. Depends where you put the zero of your coordinate system. Alright, so just by substituting this here, we know, or we just discovered, that the energy at the position R is equal to Q minus Q, let's say, times E times R. But this is minus Q times R is the dipole moment. But wait, I advanced it a little bit. So imagine now that we have two charges. Sorry for that detour. You have two charges, we just sum both of them, and we have that the energy is minus Q times E times R. I'm considering again the electric field to be uniform at that point, which is true for our dipolar approximation. You can more or less see where we are going. Let's consider the charge plus that has a position R plus, and then we will have minus Q E times the position R minus. But this is exactly minus Q E, and then this Q, I'm considering two charges, but I'm going to consider that one has Q and then the other has minus Q, right? Because we want a dipole. So this is actually plus Q, because it's minus minus Q plus Q. So this is minus Q, R plus minus R minus. But this is the difference in position between the two. So this is exactly the separation between the charges. And the charge times the separation between the charges is exactly the dipole moment. So that's why a dipole, that's how a dipole interacts with an external uniform, in this case, electric field. And this tells you the physics of what is happening too, right? Because clearly what happens is that if you have a dipole in this direction and you have an electric field in this direction, then what is happening is that in order to minimize the energy, the dipole will align with the electric field, and this is what happens in classical electrostatics. So this tells you about the physics of the system. Now, this energy describes how the external field E affects the dipole. So how the dipole behaves when there is an external field. So this is an interaction energy. One could write, just for being a little bit more precise, the total electric field is the electric field of the dipole itself, which is intrinsic to the dipole, plus the electric field that is external, let's say. That is this uniform field we were talking about. And one could write the energy as the internal energy of due to the presence of the external field, the external energy of the dipole alone, plus this interaction energy, which is the interaction energy that we just saw, is minus d, the dipole moment, dot product with the electric field. Alright, and this hand-wavely, but this justifies the way why the interaction in electrostatics is this way, is minus d times e. Okay, so if we go back to our system and we want to quantize matter, now we have whatever atom, we have the dipole moment. Now the dipole moment elevates to a quantum mechanical operator, and this will be minus the charge of the electron, in this case, times r, where r now is the operator, is the vectorial operator defining the distances between the two charges, Re. But the idea is that the interaction energy that now I'm going to write as an interaction Hamiltonian is going to take the form minus d times E. And in this case, this electric field is again classical, and the only thing we are quantizing is the atomic dipole moment, because it's an atom and it's quantized. In a further video, we will see what happens when the light is quantized and what is the difference between the classical and the quantum case. But first, let's understand what happens if the light is considered just classical. It's a simple case. Okay, so now we can write the Hamiltonian of our system, or the energy of our system, as the energy of the atom that I wrote before. I'm going to rewrite it here. And the interaction term. So the atom again is h bar omega 0, and then we wrote it in this form, and now we have the interaction term, and this is the Hamiltonian of our system. Now let's dive a little bit more into what is this dipolar operator and what is the form that it should have quantum mechanically. So let's try to see how is that form. For looking at that, we can look at symmetries in the system. In particular, we can look at the parity operator. So there is an operator called the parity operator, and I call it pi, capital pi, that transform in this way. If I apply the parity operator on the position operator, separation between the charges, but the operator one, it just flips the position operator. So you can think at it as you have the proton and you have a cloud with the electron, and when you apply the pi operator, you just get the opposite position. So one of the things we can see is that in atomic physics, the Hamiltonian of the system is of the form p squared over 2m, where this is just the kinetic energy of the electron, and then there is some kind of potential that is has some strength, and then depends inversely proportional with distance, but it doesn't care about the direction. It cares only about the absolute value of this distance between the electron and the proton. So this means, it's subtle, but it's clear that this means that the Hamiltonian of the system commutes with the parity operator of the system. So this commutator is equal to 0. This follows because the parity operator, the only reason why it exists is flipping the sign. So it only cares about the sign of this position operator. But the Hamiltonian doesn't care. So this means that they have to commute. But in particular, this means that the eigenstates of the Hamiltonian operator are also the eigenstates of the parity operator. And this will become relevant in what follows. So follow me here. So one of the mathematical properties of this parity operator is that it's a unitary operator. This can be proven. So it's a unitary operator, and typically a unitary operator is called U, so I wrote U. In this case it's pi, sorry. So the inverse of the operator pi is equal to itself, and it's also idempotent. Because of this rule here, one can show that if you apply pi twice, you just get 1, the unitary matrix, because you flip the sign twice, so you get 1. This is very important because you can show that an operator with these characteristics has eigenvalues that are plus or minus 1 only, like the Pauli matrices in a 2D Hilbert space, for example. Because of symmetry reasons, I think that group theory can also show this kind of very easily, this kind of relationships. But wait, let's examine what the consequences of what we just said. If we have the parity operator and we apply twice, we know we have minus RE. This is just the definition. But now, if we apply pi to the minus 1 from the side, or pi, just pi from the side, we get pi RE, and I would be pi plus pi, but this is the identity matrix, so it's the same. And now here we just apply it from the right, so it's minus RE times pi daga. But this means, pi. We apply pi, so this pi daga disappears, and then you get a pi here. Okay. So this is true, but this means that they anti-commute. The parity operator anti-commutes with the position, the separation position operator. So this is 0, and I put a plus here. This is the anti-commutator. But this means that if I have, let's go to the eigenenergy basis. If I go to the eigenenergy basis, so by this I just mean that I am working with the ground and the excited states, considering matter only here. And remember, we are doing all of this in order to understand the structure of the dipole operator in this case. Then let's call it A and B, two states in the eigenstate energy basis, and then we should have that if we apply the anti-commutator between E and E between two states, whatever they are, A and B, this should be 0. And this should be 0 because just the anti-commutator is 0. So this is just 0. Alright, in any case. But now, let's write this in another way. This is pi RE plus RE pi. Right? This is just from the definition of the anti-commutator. And now what happens is that since the eigenstate of H are eigenstate of pi, then if these are in the eigenenergy basis, they are also eigenstate of pi. So I can apply pi from the right, and I will get a certain eigenvalue that I will call little pi a. So this is just an eigenvalue of the parity operator. What I mean is that if I apply pi over the state a, I just get pi a times the state a. And this pi a can only be plus or minus 1, depending on the symmetry of the wave function spatially. So this is true from the right and from the left. So I get pi b, and then I get this value here. But all of this, remember, is equal to 0. So now let's see what this means. This thing here is exactly equivalent to the dipole moment, right? Because the dipole moment in essence is this separation between charges. So this is how the structure of the dipole moment is. And so what happens if, for example, I replace A and B by the ground state? So then I would have the relationship that pi A plus pi B, and now is ground state. I'm gonna say RE, but remember this is gonna be just the dipole operator B. This should be equal to 0, but this cannot be 0 because now pi A is pi ground state and pi B is pi ground state. And what I mean by that is the eigenstate associated with the ground state. So pi applied on the ground state will give me pi G applied on the ground state. And this pi G or pi A could be plus or minus 1 depending on the exact atom that one has. But if I sum plus 1 to plus 1, I get plus 2 and it's not 0. And if I sum minus 1 and minus 1, then I get minus 2 and it's not 0. So this means that the only possibility, this is not B, this is G, the only possibility is that the diagonals of the dipole operator should be equal to 0, because the diagonal of the RE is equal to 0. The diagonal, I mean the ground in this case. So the 1 component of the matrix is equal to 0. But this is of course gonna be trivially the same exact the case for the excited state. So this means that for the dipole operator has only off diagonal terms, if any. The diagonal terms of the dipole operator should be 0. So the dipole operator can only couple states between them. In this case they can only couple the ground state and the excited state. Because in particular, if I have now the GRE now is pi G pi E, this is equal to 0. Now I don't need this to be 0. It can also be 0, but I don't need this to be 0. This doesn't have to be 0 because the parity of ground state and excited state could be opposite, so that this actually fulfills the equation. And so the message is that the dipole operator can always be written, in our case that we have only 2 levels, as a certain value between the G and the E states, that is just a number that depends on the specific atom we have, so the atomic dipole strength, let's say. And then we will have only off diagonal terms, but the off diagonal terms can obviously be written as the off diagonal terms can obviously be written as GE plus EG, which are these elements of the matrix. But this is important because we have just by symmetric consideration, we have a way of writing the dipole operator of the system, which I find very beautiful, actually, because we didn't do a lot of math. We just considered symmetries and the form of atomic Hamiltonians. Yes. Now let's define a lowering operator, atomic lowering operator of the system. G is defined as this operator here. Why? Because if it does what you would think it does. So if I apply this sigma to the excited state, well, I have G, E, E, the states are orthonormal, so this is 1, so I have G. So if G couples the excited state to the ground state, and if I apply it to the ground state, then I have G, E, G, again orthonormal, this is 0, so I have 0. So this is the lowering operator for the atomic case in 2 dimensions. Alright, so this means that if I apply sigma plus to sigma, then what I get is, just by definition, E, G, G, E, which is exactly EE, which again is exactly the operator we used before for the atom. So this is just a very convenient way of writing the Hamiltonian of the system right now, because now the Hamiltonian of our system would be the Hamiltonian of the atom, h bar omega 0, and now I can just write sigma plus sigma, which is this EE. And now we have the dipole moment times the electric field, but the dipole moment we just saw that is G D E. Now this dot product with the electric field, and then we have sigma plus sigma plus. Why? Because GE is sigma and sigma plus is EG, which is exactly, if I can go up here, is exactly this. So this is sigma and this is sigma plus. Alright, so this is the form of our Hamiltonian, and now we got a structure in our Hamiltonian just by symmetric considerations. That is very nice. In order to go further, this Hamiltonian is hard, although it's simple to write, it's hard to solve in principle. So we need to do some approximation. Sorry. And the approximation we are going to make here is an important one. It's called the rotating wave approximation, or RWA. Rotating wave approximation. RWA. And to understand the rotating wave approximation, first of all, let's define mathematically new object. So this dipole moment we can also just write mathematically that it has a positive kind of part, that you will see what we mean by that, and a negative. This is what we did with the electric field. Why we write it like this? Because what we are gonna do is this, I'm just rewriting sigma plus, this is the dipole moment we just found, and we are gonna associate d plus to sigma and d minus to sigma plus, or to sigma dagger. And why is this? Because imagine we have the unperturbed Hamiltonian, and by the unperturbed Hamiltonian I mean that there is no light, so there is no interaction, there is no perturbation to the atom, so it's just the Hamiltonian of the atom, right? Then the Hamiltonian is already diagonal, and we know the eigenstates are just the ground state and the excited states. The Hamiltonian is h bar omega 0, 0, 0, 0, 1. And now here, since it is already solved, the Hamiltonian in essence, the states of this Hamiltonian are gonna be, well, the ground state in time, e to the minus I, and now the frequency, but the frequency of the frequency is the energy, and the energy of the ground state is 0, so 0t plus e, and now e to the minus I, and now the frequency of the state E is omega 0, omega 0t. This is just the solution of the Schrödinger equation when you have everything solved, basically, when your Hamiltonian is diagonal. There are these two states, this is 1, so this is G plus E to the minus omega 0t. So this is the evolution of any quantum state in the unperturbed case. And as you can see, the state, the excited state is picking up a certain phase at a rate of omega 0 with respect to the ground state. This is typical in quantum mechanics. Alright, so what is the mean value of sigma? So the mean value of sigma depends on t, is just psi of t sigma psi of t by definition. And now we can plug this, so this would be the bra g plus e to the complex conjugate, and now e, and now we have sigma, but sigma we know is GE, And now we have exactly what I just wrote before, the state, which is this. And now what is this? So the only possibility, for example, this E is gonna go away because it's orthogonal to this G. And this G is gonna go away because it's orthogonal to this E. So this means the only possibility is that there is GG, which gives you 1, and now we have E here, and now this e to the minus I omega 0 t, this is 1, so this is e to the minus I omega 0 t. And this is the mean value of this sigma in the unperturbed case, and as you can see, it goes kind of like when we decompose it, it's like a positive frequency part of the Hamiltonian, because the mean value of sigma plus, just following the same argument, is going to be e to the I omega 0 t, and this justifies why we say that the dipole moment has this form, or has some structure inside, which positive and negative frequencies, but with the atomic transition, which actually makes a lot of sense. But now this means the following: the Hamiltonian of the interaction that we just discovered before is minus d times e. But now this is minus d plus, d minus, these are all vectors, but I'm gonna forget about it, it's not important. And now e plus plus e minus, because we played that game at the very beginning of the video with the electric field, decomposing it in positive and negative frequencies. So now I have a lot of terms, no? The first term, well, 4 terms in particular, is d e plus, both plus. I will have another one that is both minus, and then I will have the combination, the plus minus and the minus plus. And what happens here is that we know that this operator will go more or less, at least its mean value, will go at e to the minus I omega 0 plus omega t. And the same is the case with this, but e to the plus I blah blah blah. While these ones will go at the difference, will go at minus I, and I would be omega minus omega 0 t, and this would go the same but with plus I. And this is just e to the minus I delta, the detuning, which is the difference in frequency between the two t. So these oscillations are very rapid, and if we consider optical frequencies, for example, these oscillations go very fast. So if we are interested only in the slow dynamics of the system, because maybe we don't have femtosecond resolution in our experiment, we can literally forget, we can discard these terms, the rapid oscillations, let's say. And discarding that is an approximation, because you are discarding some dynamics of the system. It's true that the mean value of that is 0, but at the very small scales they have an effect. And this is called the rotating wave approximation. So again, this is valid if the detuning between both systems, omega minus omega 0, is way smaller than the sum, which is typically the case. And we will talk more about the rotating wave approximation in further videos, and we will try to see what happens if we try to solve it without it, which is very hard, because I would say that, I don't know how much, but I would say that 90% of ultra cold atom physics, atomic physics, is when it comes to the interaction with matter, it's relying heavily on this approximation. So everyone uses it because it's a very good approximation, but there are some systems in which this is not true, and they are interesting systems that we will see in the future. But for now, let us stick to what happens in the rotating wave approximation scenario. Just as a note, what I'm saying here, to be a little bit more explicit, is that if we have whatever observable we want to know, and we calculate it in time, we will see that these terms that we discarded, that by the way are called the counter-rotating terms, these are called counter-rotating terms, and these are called the co-rotating terms. The name of that comes historically from the magnetic resonance people doing nuclear magnetic resonance experiments. in which there is an actual oscillations that can go with the field or against the field, and these terms are related to these counter-rotating terms. But it doesn't matter. We are replacing this by the slow dynamics of the system, so we are just smoothing this function. Because these dynamics at the small scale, time scales, at the order of 1 over omega 0 plus omega, are not relevant in our case, and are less relevant as this equation is true. Alright, so this is the rotating wave approximation. It's a very important approximation. And now here I want to make a note to finish with the rotating wave approximation. And the note is the following. Sometimes we said, for example, that we have a two-level system, but sometimes you don't have a two-level system. You actually have, let's say, a 3 or a 4 or a very complicated atom, but you are saying that you have a laser with a frequency omega that is not going to interact with any other, is very far detuned from this transition, from this omega 1 transition, let's say. So for the rest of the transition, and since it is only tuned to one transition, you say that the system behaves as a qubit, as a two-level system. It's an approximation. But this depends on exactly how much is this detuning, which is omega minus omega 0. So if it is the case that omega minus omega 0 is way smaller than omega plus omega 0, then you can make the two-level system approximation. So this means that the rotating wave approximation and the two-level system approximation are one with each other. They are not independent approximations. If one considers one approximation, one should consider also the other. One cannot consider rotating wave approximation without considering also that you could have a TLS, and one cannot consider a TLS without considering that the rotating wave approximation should be done or can be done. So they are both approximations that are similar to each other, and this is an important little note that I wanted to make, because when we will break the rotating wave approximation, sometimes we break it because we have to break the two-level system approximation. We will see it in further videos again. But okay, this finishes the rotating wave approximation. But now if we actually apply the rotating wave approximation, so we discard this term, we come back to our interaction Hamiltonian, let's say with the rotating wave approximation, but I'm not going to specify it anymore in the following. And now is d plus e minus, but we have expressions for d plus and e minus, and the opposite, d minus e plus, and well, this is gonna be g dE from before. One have sigma, and then one has the unit vector of the polarization, E0, which is the amplitude of the field, divided by 2 e to the minus I omega t. Alright. And then we will have something, I just wrote the first one, we'll write something similar, this is just the first one. We will have something similar for the second one, so that in the end what we find is that this is G, the polarization vector dot product with the dipole, atomic dipole moment, E0 divided by 2 sigma e to the minus I omega t. This I omega t is picking up from the E plus or E minus, the plus in this case, and this sigma is picking up for the D plus sigma daga e to the I omega t. And this is the form of the interaction in the rotating wave approximation and in the semi-classical model. Consider a semi-classical case. Alright, and now all this term that multiplies here is characterizing the strength of the light matter interaction, the actual strength of it. If the field is high, the interaction is higher. If the dipole atomic moment of that atom in particular is high, the interaction is also bigger. So we associate a certain energy with it, and the energy that we will associate with it, we define it literally as h bar capital omega over 2. This omega is a frequency because h bar is Planck's constant divided by 2 pi, And so this omega is called the Rabi frequency, and this is a very important concept in what follows and in general in light matter interaction. This is the Rabi frequency. So that in particular the interaction Hamiltonian under this assumption is h bar omega divided by 2 sigma e to the minus I omega t plus sigma plus e to the I omega t. Simply like that. Again with the rotating wave approximation applied in the dipolar approximation, etc. And just for the matter of writing everything, this omega is defined as minus g e d times E0 divided by h bar, and is the Rabi frequency. This times is a dot product. No, it's not, sorry. It's not a dot product. It's a normal product. The dot product is inside the bracket. Alright. And this follows that the Hamiltonian of the total system is the Hamiltonian of the atom plus the Hamiltonian of the interaction, which is simply h bar omega 0 sigma plus sigma plus h bar omega divided by 2 sigma e to the minus I omega t plus sigma plus e to the minus I omega t. And this is the form of the light matter interaction Hamiltonian that will describe the physics, which is the next thing we are going to see, and in particular the dynamics of the system. So let's jump right into it to finish the first part of this video, but there is still some things to talk about here. So dynamics of the system. What are the dynamics of the qubit under the presence of the external electric field, or light if you want, under the presence of light? So the state of the qubit can always be written in the eigenbasis, so it can always be written as Cg, or in any basis, better said. In the eigenbasis is trivially written, but we don't know the eigenbasis now because the Hamiltonian is not the amplitude Hamiltonian, it has an interaction term. But we can always write the Hamiltonian of the system in a basis, and a basis is this basis is very particularly well suited, because from here, if this Hamiltonian, if this state psi depends on time, we are absorbing all the time dependence in the coefficients. So we can solve the Schrödinger equation, and in particular the Schrödinger equation for the coefficients. What I mean by that is, if we write the Schrödinger equation, this is how this state is going to evolve. Well, it's going to evolve according to the Hamiltonian of the system that we just wrote before. And if we just apply, and I'm not going to do it here explicitly, but you can look at it yourself. If we apply the Hamiltonian of the system, which is this Hamiltonian of the system consists basically on a sigma plus something sigma plus. So we know how this affects these states, which compose the psi. So you can apply the Hamiltonian and see what happens to the equation. And when one does that, one gets the derivative of Cg with respect to time times g plus the derivative of Ce with respect to time times e. This is the left side part. The h bar just will appear in every side, so it just reduces, and the I already put it on the other side, so I'm just writing the solution to this little calculation. This is I omega 0 Ce times e. This comes from the sigma plus sigma that is going to act as e, as just giving the diagonal term. Then one will have minus I omega capital divided by 2 e to the I omega t CE times G minus one thing that is very similar, e to the minus I omega t CG times E. So this is the Schrodinger equation, just writing it down to the system. Now what we can do in order to decouple them is to project. So we can apply G, but let's apply G from the left, so the bra. If we apply it, obviously, for example, this term will cancel, no, this second term. So what we will have is something like the derivatives of Cg with respect to time, and that's all. And here this is 0, this is also 0. We only have minus I omega over 2 e to the I omega t Ce. And now projecting from the other side, we will have the derivative of Ce with respect to time is equal to minus I omega 0 Ce minus I omega over 2 capital e to the minus I omega t Cg. But this is just applying this brush from the sides. And now we get two equations, but these are the two equations for the two coefficients that we are interested in. Now these two equations are a bit hard to solve as they are right now because of these fast oscillating terms. It would be very nice to remove them. And this can be done by a simple change of variables. So one goes, this is said like this, one transform to a rotating frame at omega. And in particular, the thing we are going to do is we are going to define a new coefficient that physically has the same information, by the way, because it's the same coefficient as before, times e to the I omega t. And then for the ground state is actually the same. Now with this definition we can rewrite this equation. For example, the first equation is the derivatives of Cg with respect to time is just minus I omega divided by 2, and now it's just Ce like this. And for the second equation one needs to recall that Ce is, if this is true, then Ce is equal to Ce tilde e to the minus I omega t. So now we have to differentiate this with respect to time in order to obtain the second equation. And then one gets just that the minus I omega Ce e to the minus I omega t, this comes from the just from the derivative of the exponential part. Then well, we would have the derivative of Ce with respect to time times e to the minus I omega t, and then on the right hand side one has minus I omega 0 Ce, but Ce is Ce tilde e to the minus I omega t minus I omega divided by 2 e to the minus I omega t Cg, which is the same as the other. And as you can see, all the exponential terms magically go away, and then we got the two equations that we are interested in. I'm going to write them down because these are the equations we have to solve. The derivative of Cg with respect to time is equal to minus I omega divided by 2 Ce tilde, and the derivative of Ce tilde with respect to time is equal to minus I, the tuning. This is because in the right hand side here, this term, when you go to the other side you get a omega minus omega 0, which is this, the tuning, Ce minus I omega divided by 2 Cg. And these are the equations, again, these are the equations of motion, which are partial derivatives that are coupled. between the two coefficients that defines any quantum state. So this will tell you the dynamics of any quantum state under certain initial conditions for the coefficients. So we have to say how the atom starts, then apply the field and see what happens. And these equations are telling you what happened. And now we can differentiate two scenarios. The first scenario is that delta equals 0. So delta equals 0, the tuning is 0, means that the frequency of your laser is exactly tuned to the atomic transition. So this is called the resonant case, because the laser is resonant with the atom, with matter. Light and matter are resonant. And in this resonant case, the equations simplify to, well, the first derivative is the same, omega over 2 CE, and is the second derivative that now the first term is 0, and it simplifies to these equations here, and these equations are very symmetric, right? So these are screaming to you already that they are gonna oscillate in time because of their symmetry and because of the way, you know, a derivative with respect to time that has an imaginary part is probably an exponential with an imaginary part, which is a sinusoidal type of function. But in any case, we can just show that it is by differentiating again. We do the derivative with respect to time of the first, for example, and then we get second derivatives of Cg with respect to time twice is equal to minus I omega over 2, and now would be the derivative of C, but we can just use the second equation to decouple it, because now this equation only depends on one of the things we want to know, which is this Cg, and this is simply minus omega divided by 2 squared Cg. Now we have the second derivative of a function that is equal to the function. This is a very well-known differential equation in which, in particular, the general solution are sine and cosine, and the frequency is exactly this omega divided by 2. It has the perfect structure. Cosine of omega divided by 2t. Alright, and now one thing that we could do is to say, okay, now we want to write it, instead of these terms a and b, we want to write it in terms of the Cg at 0, at t equals 0, so the initial condition for the atom, and Ce at 0, which is more convenient. This can be done, it's just a little bit of algebra, it's very easy. So I will write just the solution here, and the solution is that Cg of t is equal to the initial condition for G, for the ground state, cosine omega divided by 2t, minus Ice of 0, this is just a number, sine omega divided by 2t. And very similarly, just doing exactly the same thing for the Ce, one gets Ce of 0 cosine omega 2t minus I Cg of 0 sine omega 2t. And this means that the populations of the ground state and the excited state are gonna swap in some case, in some sense. We can just plot it. So imagine, as an example, that our initial condition is that the atom initially is exactly in the ground state, so the probability of finding the atom in the ground state is 1, and the probability of finding it in the excited state is 0. So now, if we plot the probability of the atom to be in the excited state as a function of time, what we will get, if this is 1, is at the beginning it starts at 0, but by the way, just looking at, so Ce, in this case, with this initial condition, Ce is basically the sine of omega divided by 2t, probably multiplied by a factor minus I, that we don't care, because this probability is the modulus square of Ce, so we don't care about this minus r. So we start at 0 and we sinusoidally square, because it's sine square, goes like this. If we also, frequency of this is clearly omega divided by 2, so if we put omega t in the axis, then this is exactly pi, this is 2 pi, this is 3 pi, because again this axis is omega times t. Omega is a frequency, remember, this is 5 pi, this is 4 pi, etc. This is 0, this is 1. And this phenomena here is called the Rabi flopping. Because what is happening is that initially we had an atom that was in the ground state, and by shining light to it, it's periodically going up to the excited state, and then because we are still shining light, we are stimulating the emission, this is stimulated emission of the atom back again to the ground state. And in the middle there is a certain probability of finding the atom is in a quantum superposition between ground state and excited state. And this is very important. And this is very important because the period of this oscillation t is clearly 2 pi over omega, and so imagine that we have the atom in the ground state and we want to put the atom in the excited state. So one thing that we can do is that we can send a pulse of light for a certain time t, and if this time is exactly the period over 2, then this is 2 pi over 2 omega, this is pi divided by omega, so this is the time. But now this means that omega times t is equal to pi in this case. So if we shine for this exact time t, we can call it t pi, then after that interaction we know the atom is exactly in the excited state. So we did this operation to the atom. So we are manipulating the quantum state of the atom, we are just exciting it in this case exactly, precisely, and this is called a pi pulse for evident reasons. But we can play the same game with a pi over 2 pulse if the period is t over 4, and in this case we are exactly here in pi over 2, this is 1/2. So from the ground state we prepare the atom in a quantum superposition with equal coefficients and probably some kind of phase between the two. So we start knowing how to manipulate quantum state of matter using light, and this is the easiest way that one can do that. Now it is true as a note that here I'm considering that the electric field was constant, was uniform. But now if I send a pulse, it's not uniform. So if I send a pulse, I could imagine an envelope, and I'm sending some electromagnetic wave with a certain envelope, A of t, which would be the amplitude, depends on time. And now the condition, this is a bit more technical, but the condition is just that this integral here of omega dt, because now omega, so the interaction strength depends on time because the amplitude of the field depends on time. But if this is equal to pi, or if this is equal to pi over 2, and this envelope is known, so this can be calculated, then one has your pi pulse and your pi over 2 pulse, and it works exactly the same way. And until here is this video that we cover the resonant case. In the following video we will start by the case 2, so we will start exactly here by covering the nearly resonant case. So the case in which the detuning is not equal to 0. And I said nearly, well, I will explain in the next video why we say nearly. But for now, let's stop here. Thanks for watching, guys.